Hello, everyone, and welcome back to your channel, excuse me, of Math and Engineering Made Easy. Today, I want to go over something I mentioned before in my engineering statics course. You can find it in the description. Well, in fact, in the playlist called Engineering Made Easy. Um, and that is the directional cosines. So what is the directional or directional cosines? It says that whether you are in 1D, 2D, 3D, or multi-dimensions space, and you draw a line, okay? That line will always make angles with the coordinate axes, right? Let's take a trivial case, like if I have only one dimension, like just the x-axis, everything has to be on the x. So if I draw a line along the x, that line L makes an angle 0 with the x-axis, right? So we say cosine square theta, where theta here is 0, equals 1. We know that cosine 0 is 1. And that's why it's trivial, right? If we are in 2D, x and y, you learn what you believed. Well, it is true, but it's not the uh, identity. It's a special case of a true identity there. It told you, so if I have any line, I'm going to let it to passing through the origin. It doesn't have to, but just for simplicity, but any line will form two angles with the x and y, right? So this is theta. I'm going to call it theta for the time being. So you learn in trig that sine square theta plus cos square theta equals 1, right? But we know something. We know that the sine of this angle is the cosine of its complement. So if I'm going to call that theta sub x, and I call this theta sub y, I know that I'm going to write this sine square theta, which is theta x, can be written as cosine square theta sub y, right? Because these two angles are complementary angles. Plus cosine square theta, now I call it theta sub x, equals 1. Meaning, and that's the directional cosine, meaning if I take the angles between any line in a plane and the two coordinate axes, then the sum square of their cosines, these angles, add up to 1. If I am in 3D, so let's say this is my x, since I don't like to call this the x in 3D, but since you are used to that, we're going to keep x, y as they are, and then we are going to draw another axis here, which is the z. So if I have a line in space, notice it's not easy to draw a line in space on a 2D paper, and that's why you have to be careful here, that this line is not in the xy plane or the xz. No, it's in space. But it makes an angle theta sub x with the x-axis, an angle theta sub y. Notice these are not in the same plane. So theta x and theta y don't add up to 90 degrees. This line is like that. So theta sub x is this angle, and theta sub y is that angle. They are in two different planes, as you can see. And theta sub z is that. The law says cosine square theta x plus cos square theta y. Oops, I'm sorry. Theta y plus cos square theta sub z equals 1. So that's basically, and if you have n dimensions and you have theta making, or the line drawn in n-dimensional space makes angles theta sub 1, theta sub 2, theta sub 3, theta sub n, with the n coordinate axes, the sum square of these all cosine squares will add up to 1. But as I said, we make that in 2D, and then we say, okay, I know that the sine of one is the cosine of the other, so I can drop the subscript and call it just one angle theta. So if I have the angle that the line makes with the x-axis, this guy would be cosine and this guy would be sine, and we get what you believed is the identity in trig. Of course, it is an identity, but it's a special case of a more generic identity that the sum square of all the cosines equal 1. A week ago, I was tutoring my best student so far that I've encountered. I'm not going to talk much about him, even though he deserves a lot. But just to let you know, he's a ninth grader and he's getting ready to take the AP Calc BC test this year. That's how good he is. And then he told me, is there something called directional signs? And I say, no, I don't think so. But he said, but it works for 2D. And I said, wait a second. Oh, yeah. Sine squared theta x plus sine squared theta y equals 1. But I told him that's probably just for 2D. It doesn't work anywhere. And then right after we finished, I thought about it and I said, oh my God, he is right. But the idea is not sine square. The sum of the sine square is not 1, but it's something easy to find out. Let's assume we are, by the way, his name is Mliki Padogi. And as I said, he is my best student that I have encountered so far, better even than many of my college students or when I was teaching. It turns out that yes, sine square theta x plus sine square theta y equals 1. But when you go to the 3D, you see what would happen? I'm going to write this as 1 minus cos square theta x plus 1 minus sine square theta y plus 1 minus sine square theta z, and that should equal 1. I'm going to cancel 1 with 1. I'm going to move the signs. I'm sorry. This is sine. I'm going to move the signs to the other side, so I get sine square theta x plus sine square theta y plus sine square theta z equals 2. So it was 2 here, it's 1 there, and if I come here, the angle between L and the x-axis is 0, and sine square 0 equals 0. It keeps increasing by 1. When I was in 1D, the sum square of the sine is 0. In 2D, it's 1. In 3D, it's 2. The sum of the sine squares of theta sub n going from 1 to infinity equals n, which is the number of coordinates, like 1 coordinate, 2, 3, minus 1. So if I am in 1D, the sum square of sine is 0. In 2D, it's 1. In 3D, it's 2, and so on and so forth. That is attributed to Mliki. He is the one who found that, or he pushed me to find that, but he has really, I'm grateful to him. I thank him very much. I hope you like this, what we are going to call, between quotation mark, directional signs. And we found a law for it very easily. I should have thought of that much earlier. Thank you, Mliki. I hope you enjoyed it, and I wish to see you soon. Have a great time. Bye.